Hey dear students, welcome back to our YouTube channel School for All. So today we are still under the Advanced Level Physics program and also still under secret problems, RLC secret. So this will be the last video under secret problems. I think the other video that I can do under secret problem will be one option. The option I think is option 3. Let's talking about electronics. So that is the only video that I can do under secret problem again. And if you people have any challenging question under secret problem, you can proceed by sending it inbox or in the YouTube channel. I can still provide another video on it. So let us come back on what is interesting us today. We are talking about secret problems, RLC secrets. So we are in RL is for who? Is for resistor, L is for inductor, and C is for capacitor. So it means that when we are talking about RLC secret, we are talking about a resistor, an inductor, and a capacitor connected in series across an AC supply. So as usual, we will start with our small recall. So that you should understand the principle or the different concepts of RLC secret. Then we'll proceed now with an example to apply the concept. Now, the small recall here, so giving the RLC secret below. So as I was saying, RLC secret, I should have a resistor connected in series with an inductor and then a capacitor. All these should be connected across an AC supply. So when I'm talking about AC supply, let's call this branch A. When I'm talking about AC supply, we all know that what AC supply is a type of current that is flowing in two directions. So something like that is sinusoidal curve like this, where this one is AC still, it's also depending on time. So it means that an AC supply is characterized by two parameters. What we call a peak voltage and the peak value. So here is current, so the peak current, I will call it I maximum, and what we call the frequency. You see that anytime you have an RLC secret problem, you see that they will come and put here the peak value of AC and its frequency, because it's characterized by its maximum value and the number of oscillation per time. So that is it. But this peak value, we are not using it. It's not supplying it really. The peak value is it's rather supplying what we call IRMS, the root mean square value. So, and that root mean square value to calculate is not difficult. You take the peak value E max, you divide by root 2. So that is what he's supplying. He's supplying RLM and is having a certain frequency here. So that is it. So as I was saying, an AC current is characterized by two parameters: is peak value and is frequency. Okay, so this is our RLC secret. This is our supplier. He's supplying RLS. Then he's supplying it to each component here, R, L, and C. Okay. Now, if I want to come out now with the voltage of each component of my circuit. You see that since current is going like this, we know that the voltage will go in the opposite direction to the current. So here will be VR, here will be VL, here will be VC. On the diagram now, let us come out with the different voltages across each component. Of the circuit. Okay. Now, the first one, we all know that what? Voltage from Kirchhoff, from Ohm's law. stop, and then we all know that voltage is given as a certain current I times a certain resistance R. So if I want to calculate the voltage across my first component is resistor R, is simple, is our resistance R times IRLS. Now, if I want now to go to the next component of our circuit, which is the inductor, I will take the voltage across L, will be what we call, this is the resistance of the inductor. We don't call it R, no. The resistance of the inductor is called inductive reactance. And you see that it's having its own formula. It's having its own formula because it's having also a particular frequency. Yeah. So SL times IRL is where XL is simply equals to what we call angular frequency times L, which is the same as 2 pi L, because angular frequency is 2 pi F. And let me give it the name, it's called inductive reactance. Inductive reactance. And it is measured in SI unit is ohms, showing that what is still a resistance. So that is it. Now let us proceed with the last component. Our last component of the circuit is the capacitor. So the voltage across the capacitor C, is simply equals to now XC. So I think you can imagine already, if this one is SL, it's called inductive reactance, H should be called capacitive reactance, and our current IRS. So it's now here we have 1 over omega C, which is same as 1 over 2 pi C, and the name is capacitive reactance. And since it is still a resistance, it is measured in SI is still ohms. So that is it. Those are the different voltages of our circuit. So you should be capable to crank all these formats. You should be able to calculate the voltage across the first component, which is R, the voltage across the inductor, the voltage across the capacitor. So after coming out with the different formulas to how to calculate the voltage on each component of our circuit, now let us proceed and let us see how we can come up with a formula if you want to calculate the PT or the voltage between these 2 points AB. It's okay. You see that you can think that if I want to calculate the voltage across AB, I will solve the voltage. No. I will explain you why it will not be correct. When we do an example, it's not correct. That you are saying that VAB is V R plus V L plus VC. No, it's not correct, because you see when we do phasor diagram, I will explain. You see that they are not in phase. They are not in the same phase that you can add them like algebraically. No, the only way to add them is what we call vectorially, or using the phasor addition. So we'll talk about it after. So it means that the voltage across AB is simply equals to Z. Z is called the impedance of the circuit times IRLS. So that's it. So Z is still what? It's still having the unit of a resistance. Yeah. And I is current. So that's it. Dz, I will show you how to come up with Dz. It's not the addition of all the resistance. No. It's a vectorial addition or a phasor addition of all the resistance of the circuit. So that is it. Now let us proceed with the phasor diagram. As I was saying, it's with the phasor diagram that will come out with Dz. That's what we're talking about. Therefore, with Dz you can find out VAB. Okay. Okay, so let's talk about phasor diagram. So the phasor diagram is that diagram that represent what? It represents the different, let's say what, the different phase. Yeah, it represents the different phase existing between the current flowing in the circuit and the different what? Voltages. So that is it. It represents the phase different because they are not all in phase. Yeah, I think that you people should know that. If I take the voltage across R is in phase with the current. Is in phase with the current. But if I go now to the voltage across L, you see that the voltage across L is not in phase with the current. No. The voltage across L, the inductor, is in phase different of 90 degrees. Is in phase different of 90 degrees with the current. It's a phase different of 90 degrees with the current. It means that what? It means that it leads the current by 90 degrees. It means that VL leads RMS by 90 degrees. Now let us go down to the voltage across C. You see that the voltage across C is in phase different. It's in phase different of negative 90 degrees with the current. Meaning that what? Meaning that it lags. So VC lags IMS by 90 degrees. Meaning that it's behind. Last one is behind. It's behind by 90 degrees. Yeah. With respect to the current. So that's it. So with this phase difference, you are now understanding why if I add these two, they are not in the same phase. If I add VR, VL, VC, I can never come out with VA, AB. No. You cannot add values that are not in phase. Yeah. It will not make sense. So in order for us to add it, we should do a vectorial addition or what we call a phasor addition. So let me first of all come out with a phasor diagram. Let me come out with a phasor diagram. Okay, so this is a phasor diagram. I will have a phasor diagram. You should first of all start by representing. You choose your what we call the reference axis. The reference axis here is it. So I will call it the phase axis. The phase axis, and that phase axis represents what? The axis for current. Okay, I start. How is VR with what is the phase difference of VR with current? It is what? In phase. It means that they are making an angle of 0 degree. It means that VR is simply found on this line because they are making an angle of 0 degree. They are on the same axis, same line. Now when I go down to VL, you see that VL is in phase different of 90 degree. 90 degree means I should form an angle of 90 degree. You see that it is somewhere here. I should form an angle of 90 degree. You see that it is somewhere here. Yeah, this is our VL, which is XL times IR Here it is MS. So this is the 90 degree. Now when I go down to the voltage across the capacitor, it is phase different of negative 90 degree. When you measure an angle of negative 90 degree, you go down like this. So you will bring us down. Like this to show that this is VC, which is XC times RMS. So that is it. There's a phasor diagram. Therefore, we can now call the resultant voltage. The resultant voltage will be this one, comma VA, which is equal to ZIRMS. So that is it. You see, this is the phasor diagram representing this. They are offering the information and just from giving. So that is it. And therefore, this is theta. Let's say phi. That represents the phase difference. So now, with the phasor diagram now, we can now come out with the value of the phasor diagram, with the phasor diagram, I can now come with the value of the PT across the branch AB, and I can now come also with the phase difference between the current and AB. So I'll start. So if you want to calculate the PT or the voltage across the branch AB, as I was saying, it's a vectorial approach. Yeah, it's a vectorial approach or a phasor addition that we are doing. So if I want to find VAB, you see that VAB is simply equals to what? Look at this, is a right angle triangle. This is a right angle triangle. With the opposite of the angle here, it should be what? I go up, I go down. It means that it should be XL minus XC all 2 times the current I on S. As simple as that, because SL is giving us up, SL is giving us down. So if you want to find the value here, I will take this one minus this one to have this one. So that is the opposite. So you see that I'm having a right angle triangle. So if I want to calculate VAB is what? Is the resultant. Yeah, the resultant voltage of this right angle triangle. And therefore, from Pythagoras theorem, we all know that VAB square be equals to VR square plus bracket VL minus VC all square. So we all know that VAB square is simply equals to what? Is ZI max all square equals to RI max all square plus XL minus XC I max all square. Consider this one will cancel, and cancel. So I'll be left with Z square equals to R square plus XL minus XC all square. You see how the impedance is coming out? Therefore, my impedance is simply equals to what? Square root of R square plus XL minus XC all square. So this is the value of the impedance of the circuit. With this value of the impedance, I come directly and replace it here. I replace it. And these are VAB is equal to ZIRN. So if I have the value of the impedance Z, I have IRMS, the root mean square value of the current. I can calculate what? The resultant PT across the branch AB. Now, as I was saying, in an RLC circuit, there's what we call a phase difference. Yeah, because they are not all in phase. There's a phase difference between the current flowing in the circuit and the resultant PT. I'm not having the circuit here, as we were saying. So let us come and calculate now the phase difference. Now you will see now, if you want to calculate the phase difference, between who? Between the current and the voltage flowing in the circuit. I'm still considering what? I'm still considering my right angle triangle. Under what? I'm having this value. I'm having the opposite and the adjacent. Therefore, I will use which trigonometry ratio? Tan. So it means that tan phi is simply equals to opposite. Opposite will be x L minus x c. I will cancel, no need to put it again. Divided by r. So therefore, phase difference is simply equals to tan inverse of SL minus SC divided by R. That is the phase difference of the circuit. The phase difference or the angle formed between the phase axis, which is the current, and the voltage, the resultant voltage. So that is it. People should cram those formulas. Yeah, we should cram it. The impedance is inside the formula booklet. And also phi. Again, if it's not inside the formula booklet, it's very difficult to cram it. All know that is the opposite of this our triangle, and this one is adjacent. Now let us see the consequences the consequences on on the phase difference when SL and SC vary. Okay, I can wipe here. Let us do fast. Now, take this one note. We see about first condition. If the inductive reactance is greater than the capacitive reactance, we also that tan phi be positive implies phi is positive. Tan phi is positive, it means that phi is positive. And what is the consequence of that? The consequence is that the secret is said to be net inductive. So let's say the secret is more inductive than capacitive because the inductive reactance is greater than SL. So the secret is said to be net inductive and as a result when phi is positive as a result, VAB, the resultant which I call the branch AB, leads the current I leads RMS by 90. Okay, we don't say 90 degree because we don't know. The RMS by an angle 5. Lead means that it is in front. Yeah. So when phi is positive, it means that VAB is in front, as exactly the diagram that we are having here. You see that VAB was in front. See, was on top of our phase axis, our current axis, like this on top, because you see that this one was greater than this one. So we stay on top of the current axis. Now, if we now go to the other condition, if XL is less than SC, we consider what phi is negative. You see that here phi was positive, so we measure it like that. Now phi is negative. When phi is negative, what happens? You see that when phi is negative, the secret is said to be net inductive. So the secret is net capacitive. The secret is said to be net capacitive because SC is greater than SL, so the secret is more capacitive than inductive. And as a result, this implies that the voltage across AB lacks the current RMS by 5. And you see that the phasor diagram now here will be this one goes up. This is the axis of current. Since this one is greater, it will cancel until we see then go down again. Since it is greater, this one is XL, SC. So that the result now is something like that. This is the angle which is negative. Remember, angle like that is negative. You know it. Then you see that what? You see that our VAB is under who? I. It's under the current axis, therefore it lags, it's behind. So that is it. Or let's say current now leads VAB. You can say current leads VAB or VAB lags the current. So that is it. So those are the consequences on when the value of SL and SC changes. Now let us go now to the most important one, resonance. Okay? At resonance, when we are talking about resonance, it means that what? A maximum amount of current is flowing in the circuit. So at resonance, maximum current flows in the circuit. Anytime you are inside the equation, they are talking about find this when maximum current flows in the circuit, means that it's at zero. That is a condition for maximum current to flow in the circuit. Now, this happens when XC is exactly equal to SL. So when the capacitive reactance is equal to the inductive reactance, we say that we are in resonance. And as a result, we have W, as a result, we have 1 over WC is simply equals to WN. So by cross multiply, we have W squared CL is simply equals to 1. So W is simply equals to square root of LC. So this is the angular frequency. Now if I want to come up with the frequency, another 2 pi f, W is 2 pi f, W equals to 1 over square root of LC. Therefore F is simply equals to 1 over 2 pi square root of LC. It's what we call in French a frequency pop. There is it. W0, F0, this is the frequency at resonance. The angular frequency at resonance. So that is the consequence when SC equals to SL. It's okay. And from there also you see that the impedance in the CP is simply equals to R. Because we under that impedance we square root of R squared plus XL minus SC. If these two are equal to 0, therefore impedance is simply equals to R, which implies VAB now become easy to calculate. It is simply equals to what? I RMS R. So VAB here should also be RMS since it is a root mean square current here, therefore it means that you are calculating the root mean square voltage. So that is the consequences of SS being equals to XL. Of S equals to SL. Okay. Let us go to the last important point of our record, the power absorbed by the circuit. In fact, who is absorbing power there? I think it's the power absorbed by the resistor. Okay, let us proceed now with the last important point of our record, which is the power absorbed by a resistor in an RLC circuit. So power absorbed by a resistor in an AC circuit. Okay, that power, simply we know that power is IV, right? So here will be I, the power will be I RMX times V RMX. And we all know that RMX is what? Peak value I max times V max divided by square root of 2 times square root of 2. So it's simply equals to I max times V max divided by 2 times 2 is 2. So that is the power absorbed by a resistor in an AC circuit. Okay, so then let us proceed now with example 1. Now to apply the small recorder we are just conveying. So we are having a sample DC equation here. This is the circuit diagram. So the question is saying an LCR circuit consists of an inductor. This is the inductor of inductance 200 microhenry, a capacitor of capacitance 120 microfarads, and a resistor of resistance 100 ohms, all connected in series and powered by an AC source of peak voltage. So this is the peak voltage, gain 12 volts, and a frequency of 50 Hz as shown below. As I was saying, when we are having an AC supply, it's divided by two parameters, the peak voltage and the frequency. So the first question here is asking us, A, state why the voltage across each component of the series circuit above does not sum up to the total input VRN. So we are asking why is it that if I sum all this, the voltage across each component here like this, so VL, VC, VR, if I sum them, it will not give us VRNS. So the root mean square voltage. As I was saying in the record, the algebraic sum are not the same because they are not in phase. So the only answer is that we will not give the same thing because all those voltages are not in phase. They are in phase difference. Yeah, they are not in phase. So therefore the sum cannot give us VRNS. VRFS. So that is it. So let us write it. So this is because the different voltage across each component, the different voltages across each component are not in phase. That is it. So the only way for us to sum all those voltages so that it should give us the resultant voltage is to do vectorial addition or phasor addition. If you do algebraic addition, it will not be the same because they are not in phase. So there is the A part of the equation. Let us proceed with the B part. The B part, you are asked to calculate Roman 1. Calculate Roman 1, the value of voltage VRS. So you are asked to calculate VRMS. VRMS, Wood square value. As I was saying, inside the record, we all know that one. VRMS is equals to the peak value V0 or Vmax divided by square root of 2. Now, are we having the peak value of VO? Let us see from the data we are having here. Yes, let us put the data here. The data we are having here, we are having V0 equals to 312 voltage. We are having the frequency F equals to 50 Hz. So these are the characteristics of the AC supply, in fact. Now let us come and substitute here. It means that V0 will be 312 volts divided by root 2, making VRMS to be slightly equal to 220 volts, exactly as the voltage that ADO is supplying us. So it's slightly equal to 220 volts. So that is as easy as that. You come out with the voltage, supplied by the supplier. Now let us go to Roman 2 of the B part. Okay, Roman 2 is asking us to calculate the impedance of the circuit. So we want to calculate Z. We all know that Z is the impedance of the circuit. We all know that what? Impedance, Z. The impedance of the circuit is square root of R squared, R squared plus what? The inductive reactance minus the capacitive reactance all squared. So that is it. So the first step here, I'll first of all come and calculate what? I will calculate SL. Let us calculate SL. Another SL is omega what? Omega L, which is the same as 2 pi frequency L. Now 2 pi times frequency 50 Hz times L. L is how many? 200 milli. Milli means times 10 to the negative degree times 10 to the negative degree Henry. So 62.8 ohms. As I was saying, it is measuring in ohms. Now let us proceed with SC. The other S is 1 over omega C. So I'll have 1 over 2 pi times 50 Hz times, now C is how many? C is 120 microfarad times 10 to the negative 6 farad. So after the numerical application, equals to 26.5 ohms. So it's value equals to 26.5 ohms. Now from there, you can now calculate the impedance of the circuit. So let us come and replace. So the impedance of our circuit now is simply equals to square root of 100 all squared plus in bracket 62.8 minus 26.5 all squared. So but after numerical application, you you have something like 106.4 ohms. So that is the value of the impedance of our circuit. As simple as that. So let us proceed now with Roman 3. So Roman 3 is asking us to calculate the phase angle. The phase angle is the same as calculating the phase difference. Phase angle. Okay, we are asking us to calculate the phase angle. Same as the phase difference. We all know that what? We all know that from the formula we are having tan phi is simply equals to XL minus XC all over R. This implies phi is equals to tan inverse of, I was having this value already, XL minus SC, we calculated it. It gave us 62.8 minus 26.5. all divided by 100. So after numerical application, you see that you are fine. The angle, the phase angle will simply equals to slightly equals to 20 degrees. So 20 degrees. So that is it. As simple as that, you don't waste time. Apply a formula, you replace the values, punch it, come up with the answer. Okay, students, now let us move to the Roman 4, our question. So Roman 4 is asking us the frequency for which the current in the circuit is maximum. So we want the frequency for which current is maximum. We want the frequency for which current is maximum. We all know that one. The condition for the current to be maximum inside an AC circuit is that the circuit should be at resonance. So at resonance, we know that XL equals to SXC. So as a result, we have omega L equals to 1 over omega C, which implies omega square when of course multiply equals to 1 over LC. Okay, and we all know that omega is what? Omega is 2 pi f all square is equals to 1 over LC. So our frequency at resonance is simply equals to 1 over 2 pi square root of LC. So it is already the recall. Now from here, I will now substitute the values. I will have 2 pi times square root 200 times 10 to the negative 3 Henry times C, which is 120 times 10 to the negative 6 farad. So after numerical application, we will find that the frequency at resonance is simply equals to 82.5 Hz. So that is the frequency at resonance of our circuit. Okay, now let us go to the last part of our question, which is asking us to sketch a phasor diagram to represent the phase difference between the voltage RMS and the current RMS. Okay, that is Roman 5. Okay, so Roman 5, we have to sketch a phasor diagram to represent the phase difference existing between the voltage across the circuit VRMS and the current IRMS. So that's it. Now we all know that what? We all know that the phasor diagram, first of all, represent my phase axis. As I was doing, I first of all represent my phase axis, which is the axis of current. Then we all know that the voltage across the resistor R is what? It's in phase with the current. So I will have VR here, which is equals to R times IRMS. We all know that the voltage across our inductor Vn is in phase different of 90 degrees. This is phase different of 90 degrees. So here we have SL times Rns, and we also know that the phase difference between Vc and the current is negative 90 degrees, so I will go down. So Vc times Rns. So this is our resultant. Therefore, this is the phase difference between the current and the resultant voltage, which is how many? 20 degrees. This is V Rns. That was slightly equal to 20 volts. So we are left now to calculate this one. This one will be V M minus Vc. To calculate is not difficult. To go and find, let us find IRNS. IRNS is equal to VRNS divided by Z, is the impedance. So VRNS is equal to 220 volts, and the impedance is 104.6 ohms. Okay, and the impedance is 106.4 ohms. That's it. So after numerical application, you come out with slightly equal to 2 amperes, something like that. So you come now and replace it here. It means that VC is simply equal to how many? VR, first of all, is simply equal to, so VR replacing the value of 2A here, and the value of our resistance is 100. We have slightly equal to 200 volts here. Here, when I subtract the 2, I will have slightly equal to 73 volts here, and then VRS is 220 volts. So that is the phasor diagram to represent the phase difference between the current and the voltage RMS. So that is it. That's all about the question. So this is our phasor diagram here. This is it. And then you put the values of the different voltages to complete the diagram. So that will be all about example 1 of RLC secrets. So we are together. Thank you for watching the video.